We all have a friend who's a little bit different, and mathematically, the tangent function is a little bit different. Okay, so how does this graph work? Well, very similar to cosine and sine in some ways, with a few variations. Okay, this plus c is the vertical translation. This plus b is the horizontal translation. This n value here affects the period. Okay, so how often tan repeats itself. This a value, though, is or represents a dilation from the x-axis. It also represents a whether it's reflected in the x-axis or not, whether it's positive or negative. But we don't call it the amplitude. So a tan graph doesn't have amplitude. So tan has a period, how often it repeats itself, and tan will also have these things called asymptotes in it. We've seen them before. All right, so for tan, one complete cycle of the function is pi or 180 degrees. Now, why is that? Well, to help us out to visualize what tan looks like, I've just got this GeoGebra applet, I suppose. All right, so you can see here then when theta is equal to 0, where is it going to hit the tangent at 0? We start to increase. We're just noting where this value here hits the tangent. So at 36 degrees, 0.27 is where it's going to hit the tangent. At 45, we know it's going to be 1. There it is there at 1, so it's going to hit at 1. And if we keep going here, what's going to happen is tan is going to get massive. Okay, so where it hits the tangent line along here is absolutely massive. So 87 degrees, tan is like it's way up there. All right. So what happens at 90 degrees? Well, we know that tan is undefined at 90. Okay, so we know that. So let's hit 90 and note that at 90 degrees, it's undefined. Now, when I go past 90 degrees, what it's going to do is it's going to be over here somewhere. Line goes down here and it's going to be really, really negative. Okay, so what's going to happen is this graph here is going to flip-flop from positive infinity all the way down to negative infinity in the space of being either side of 90 degrees. All right, so talk about sort of all over the place. So there it is at 93, and you notice here what's happened is it's a tan value way down there. And the closer, so the more I move this across, the closer the angle, the value of tan is going to get back to 0. So if we look at it, it's going to come back soon. Here it comes, here it comes, here it comes. And it swings in to 180, it goes 0 again. Now, what happens, and this is why the period of tan is pi, is if I continue it on now, okay, it'll redraw this first section again. Okay, so it's going to go up to 270. So you can see here between 90 and 270 will be one complete cycle of tan. All right, so that's what it's going to look like. It has this sort of nature. Now note that this isn't an inflection point. It's not a gradient. It is an inflection point. It's not a stationary point of inflection. So that's not a point where it's 0 gradient. So it sort of cuts through and then continues back up again. And what tan will do now is go back to being negative again and swing all the way back in to 0. There it is there. Right, so that's the behavior of tan. So fairly chaotic function. Right, there's a method to get the equation for asymptotes of tan. So it's x equals scale plus k times period. Don't even know what that means. Won't need to do it. Okay, so let's just sketch the basic tan function. All right, so our period for this tan function is going to be pi. Our scale, what we do is instead of dividing by 4, we divide by 2. Okay. All right, so our scale is going to be pi on 2. So here we go at pi on 2, 2 pi on 2 of pi, and 3 pi on 2. And let's go to 2 pi. All right, now what happens, first of all, with tan is we go tan of 0. Well, that's going to be 0. Tan of pi on 2 is undefined. Okay, so what's going to happen is this function here is going to cut through there and approach positive infinity. So we're going to write or put in an asymptote along here, which is x is equal to pi on 2. All right, and what it's going to do is it's going to asymptote every pi. So we're going to get one full repetition of tan between pi on 2 and 3 pi on 2. So the next asymptote will, or should be at 3 pi on 2. And if you're wondering, try to find the tan of 3 pi on 2. It's undefined there, so that's why it's asymptotic there. All right, so what we're going to do is sort of swing it up on maybe a 45-degree angle. Nope, just get the asymptote. Like so. All right, now over here, it's going to cut through through pi rather. So it's going to come in like so. All right, so you want to have it roughly symmetrical about like, so this shape here should look the same as if it was rotated 180 degrees and went down there. And that part there should look like that part. Now this part here is the negative portion up to here, so we're going to go all right, up to there. That's what tan essentially looks like. All right, so again, its behavior is a little bit bizarre. Well, not bizarre, it's really predictable actually, but it just looks bizarre. All right, so let's sketch one. Okay, so sketch a graph of the following functions labeling the coordinates of axial intercepts, endpoints, and equations of asymptotes. So we want it over 0 to 2 pi. So we're going to note here that the period of a tan function is usually, I'm so in the habit of putting 2 pi down, the period is pi, and this one here is, or has an n value of 2, so we're going to go pi on 2. The scale, remember, we've got 2 key points to put in here, so we're going to go pi on 2 over 2, which is pi on 4. So that's going to be our scale is pi on 4. All right, ready to draw up the Cartesian plane. Okay, now, so let's label our scale, pi on 4, pi on 2, 2 pi on 4, 3 pi on 4, pi, 5 pi on 4, 6 pi on 4 is 3 pi on 2, 7 pi on 4, 8 pi on 4 is 2 pi. All right, so what's going to happen is that tan will start there and will asymptote at pi on 4. Now remember, our standard tan function asymptotes at pi on 2, but because of the period change or the dilation factor being half from the y-axis, what that does is halves the period, but also grabs all of the asymptotes and pulls them in, okay? So when is it going to be asymptotic next after this? Well, it's not going to be every pi, okay, because the period is now pi on 2. It's going to be every period, every pi on 2. So if I've got pi on 4 and I add pi on 2 to it, that's 2 pi on 4. That'll take me to 3 pi on 4. And there's our next asymptote, 3 pi on 4. We got 5 pi on 4, 7 pi on 4, 9 pi on 4, etc., etc. All right, so now all we do is we just do our best effort to get something that looks tan-ish. Zero, 0, 2 pi, comma 0. Our asymptotes x is equal to 7 pi on 4, x is equal to 5 pi on 4, x is equal to 3 pi on 4, x is equal to pi on 4. Intercepts, pi on 2, comma 0, pi, comma 0, 3 pi on 2, comma 0, and already labelled. All right, so yeah, not an easy one to sketch tan. You do need to get used to it and how it behaves, but once you see it, it doesn't, and have a bit of practice with tan, its behavior is actually quite predictable. Okay, our final sketch comes from this tan function here. So what we'll note is that the horizontal translation isn't pi on 4 to the left. So let's rewrite this function as y equals tan and yank the 2 out as a common factor, x plus pi on 8. So we're going to note that what this will do is shift the graph pi on 8 units to the left. This here represents a dilation factor factor half from the y-axis. So let's note that the period, which would be typically pi for a tan function, will be dilated by a factor of a half, or our period becomes pi on 2. Our scale is going to be pi on 2, which means it's pi on 4. But because our translation is pi on 8, what I'm going to do is write our scale in as 2 pi on 8. So every 2 pi on 8, we're going to get a key feature for tan, either an asymptote or an x-intercept. All right, Cartesian plane. Okay, let's start sketching. Okay, so there's going to be heaps of points here. So we've got to draw up to 16 pi on 8. So there's going to be 16 notches. So give yourself enough space to get this in. So this is going to be pi on 8. This is going to be 2 pi on 8, which is pi on 4. 3 pi on 8. 4 pi on 8, which is pi on 2. 5 pi on 8. 6 pi on 8, which is 3 pi on 4. 7 pi on 8. 8 pi on 8, which is pi. 9 pi on 8. 10 pi on 8, which is 5 pi on 4. 11 pi on 8. 12 pi on 8, which is 3 pi on 2. 13 pi on 8. 14 pi on 8, which is 7 pi on 4. Oh. Okay, let's extend that line a little bit longer. Okay, where was I up to? So 13, 14, 15 pi on 8, 16 pi on 8, which is 2 pi. All right, we got there, didn't we? All right, so now remember what we do is we usually just sketch y equals tan 2x, first of all, and then we worry about the translation pi on 8 to the left. All right, so tan typically would start at the origin, and it's going to go up, and it will asymptote, first of all, at pi on 4. Okay, now it would usually, so the standard y equals tan x function will asymptote at pi on 2, but because it's a dilation factor half from the y-axis, what it will do is halve that and get it down to pi on 4. So there's our first asymptote. Now I'm just going to draw that small. I'm going to draw a full asymptote. So what it will do, tan will go up there. The next asymptote is going to be, so in the last one you'll note that what we did was put 0 there and then another asymptote, so every second. But remember, our scale is every 2 pi on 8, which means that every 2 pi on 8, we get a key feature. So this will be an x-intercept, and what we should get here is another asymptote. Now let's just test it. All right, so we're going to sub y equals 3 pi on 4 there. 2 lots of 3 pi on 4, which is y equals tan of 6 pi on 4, which is tan of 3 pi on 2, which is a very good sign because it's undefined, and that's what's happening at the asymptote. So it's every 2. So key feature, key feature, key feature, key feature, key feature. All right, now remember, our job's not done because what we need to do is move everything pi on 8 to the left. So grab a different color now. And this point here is going to move over to here at negative pi on 8. So what would happen usually is it's going to come up like that, but it would start coming up there, and then it's going to continue through to an asymptote, but the asymptote has also moved. So that asymptote will be along there. Now this asymptote will also move to here, to there. Whoopsie, wrong one. You see, this one's a tough sketch, all right? But I'm having to really think about these values. asymptote there, and that's it for asymptotes at the moment. Right, so what would happen is tan would usually go up towards that asymptote, so it moves over, goes up towards this asymptote here, and let's rub this part out because we don't need it. Right, and so we get an endpoint here. Right, that will move to there. So what will happen is tan comes up like so. That point goes to there, like so. That to there, that to there. And we're going to chop it there. All right, so let's start labeling what we do know. So this is the asymptotes. So it's x is equal to pi on 8. X is equal to, what's that? 4 pi on 8, 5 pi on 8. X is equal to 9 pi on 8. X is equal to 13 pi on 8. All right, so there's all our asymptotes labelled. All right, our x-intercepts, 3 pi on 8, 0, 7 pi on 8, 0, 11 pi on 8, 0, and 15 pi on 8, 0. All right, now what we've got to do is just label these endpoints here, okay? So to do that, what I'm going to do is simply put 0 into the function, and that'll get me the y-intercept. So y equals tan of, that becomes 0, and it's just tan of pi on 4. Now tan of pi on 4 is just 1, so that's when x is 0, y is 1. Now if we look across here, what this should be is it should be symmetrical. So this point here should also be 2 pi, 1. All right, and let's just try it out. So we've got tan of 4 pi plus pi on 4. So what that basically is saying is go 2 pi, 4 pi, and then another pi on 4, and calculate the value of tan, and that's going to be 1 as well. So there it is there in all its glory. It's pretty messy looking, and that's a really tough sketch, that one. So hopefully you followed on with that. Now go ahead and practice a few sketches of tan in exercise 14L.